Everyone, welcome to Composability. So today's topic is device meshes. So I've been telling everyone about how everyone on the PyTorch team needs to know more about distributed. So this is my excuse to force you all to suffer through a lecture about device mesh. And, what is it? What are some properties it has? And then go straight into there's a bunch of ongoing discussions about extensions to device mesh. So there's a thing going on where Junjie and Luca are trying to rewrite device mesh so it's done using Qt layout. So we'll talk about that. There's also an ongoing discussion about how to use the new flatten API, where you can put two mesh dimension axes together for torch titan stuff. So hopefully we can get there. But basically my goal is everyone in this meeting should understand what device mesh is, should understand what Qt layouts are. Okay, maybe that's a tall order, but feel like they understand at least. And understand what is going on with the communications and the local ranks and all that stuff. And we can go from there. So I want to field as many questions as possible while we're going here. So to start things off, let's just talk about what a device mesh is. So I want to just refer to a recent blog post that I wrote called the Parallelism Mesh Zoo, which I think is sort of a high-level description of why we care about device mesh, right? So why do we care about device mesh? Well, the idea behind a device mesh is, when you're doing large-scale distributed training, you have a ton of GPUs, and you want there to be some structure on these GPUs. You don't want just an undifferentiated slurry of 1024 GPUs. So there's a physical aspect to why you want to do this, right? So if we're talking about NVIDIA GPUs, these GPUs are organized into nodes of 8 GPUs each. And so you want something where you want a way to look at the structure of your GPUs where you can say, well, these GPUs are in nodes of 8 GPUs. And then beyond that, you have everything else. So how would you represent this kind of organization? Well, a 2D tensor is good for this, right? You say the inner dimension are the GPUs that are closest to each other. Its size is 8. And so I have 8 of these GPUs. And then the outer dimension is just how many nodes I have. And this is the veriest, simplest physical layout I can do in this situation. But there's other reasons you want to split up the device mesh as well. So let's say you're parallelizing your model. So at a very high level, the name of the game when parallelizing the model is you want to find some data that you can shard over. And by splitting the data, you now can parallelize your compute over multiple machines. So classically, we do data parallel, right? You're running a batch of computation, and you just go ahead and split up the batches and then run them on different machines. But what do you do if you have so many GPUs that you don't have enough batch dimension left? You've run out of batch dimension to split. Your batch dimension is 1024, but you're running on 4K GPUs. So how do you split things up even more? Well, if you can't split the batch dimension anymore, go find some other dimension somewhere, maybe the hidden, feature dimension on your weights, and split on that. And so you can see that, as I do more and more splits, they may be on different places, and I once again need some sort of structure in this situation. So the device mesh is all about, I have a number of device mesh dimensions, and then each device mesh dimension I can talk about, this is about doing this split. So I have the dimension is size 256, so I'm going to split this dimension over 256 size fibers. Oh, we'll get there in a moment. And then there's another thing I want to split, and that's a different dimension. And when you split things together, that's concatenating your sizes together, right? It's a sort of cross product type affair because it's exponential. Every time you split something, you are cutting the space of GPUs in half. And so I want to convey this intuition more in the rest of this meeting, but this is the sort of high level. Do we have any questions about the motivation behind device mesh? Okay, cool. Because hopefully this is all old hat for most folks here. So let's talk about let's see, how do I want to organize this? Yeah, okay, so let's talk about one particular operation you want to do with device mesh and just walk through this in detail. So the question here is essentially, so a device mesh is oh yes, Gojus.
Are device meshes used/useful without Dtensors?
Yes, you can. Like, so given a device mesh, you can ask for the PG corresponding to a device mesh dimension, and what it'll do is it'll like do all the math needed to like figure out what exactly this PG should be. And we're going to work through this math right now to like get a
Is
better
that is
understanding.
that is that a use case today where people like set up these device messages just for use, like to help them track which dimensions and which process groups are used?
So very concretely, okay. So first, I want to first a most truth. Dtensor is a really really good abstraction for working with device mesh. So I rarely see uses of device mesh without Dtensor, but they are not inextricably linked. For example, if you're doing pipeline parallelism is an MPMD abstraction. You're doing different things at every pipeline stage. We usually still put the pipeline parallelism in the device mesh as a dimension. But it's like, it's this thing where some of the device mesh dims are SPMD and some of them are MPMD, and they like get handled differently. And I want to actually, this is one of the things I want to cover. I want to talk more formally about what this difference is. But that's the flavor. Thanks for the question. Okay, so let's talk a little bit about the math that goes on inside the device mesh. So the most basic operation that you're interested in when you're working with a device mesh is the device mesh is this ND tensor that, you know, that the contents of which are like 0, 1, 2, 3, 4, 5. They're the indices of your GPUs. And this is not our underlying collectives, our nickel collectives, all those things. They know nothing about device mesh. The abstraction you have at the collective layer is instead, I have a group of ranks, and this is mediated by this thing called a process group. So if you have a bunch of ranks and you want them to talk to each other, you create a process group, spanning over those ranks. So if you're like doing FSDP, right, your process group is going to be the entire world of all the GPUs that you're all gathering the shards from. But if you're doing device mesh style computation, the set of ranks participating in a particular collective group may not cover the entire world. And in fact, this is like one of the reasons why we use device mesh. It's to like reduce the number of nodes that are talking to each other at any given point in time. So my question for you, and please think about it a little, is if I have a device mesh and I have and I say I want to do a operation on a particular axis, what GPUs talk to each other when I do this? And so we have got this 2D example, and let me go ahead and put it in a 2D form, right? So we're going to name this axis X, and we're going to name this axis Y, right? And so when I say I want to do communication on the X-axis, who talks to each other? How do I figure this out? And the 2D is a little like it can be a bit misleading actually, because some of the behavior that goes on isn't obvious until you go 3D. So to add some physical intuition, let's make this grid a little more non-trivial. So we're going to say that instead the X dimension is going to be the intranode dimension. So it's got 8 elements. And we're going to say that the Y dimension is the intranode. Right, which talks about communication across nodes. So this is all the things in one GPU. This is all the things all on the second GPU. So now hopefully it's intuitively obvious who communicates. So if I want to do a communication on intranode, I need a intranode as an inside of a node, then clearly these are all the GPUs that'll communicate with each other. And these are all the GPUs that will communicate with each other as well. Okay? So I'm doing this sort of, I'm doing this weird sort of thing. Because normally if I want to slice a tensor on the intranode axis, I would say, okay, well, give me the values at 0, and that would be 0, 8. But I'm doing sort of the opposite thing, which I'm saying is take everything that is not the intranode axis as fixed, and then vary the value of intranode, and this gives you the fiber that says what the communication you want to do is. I did a horrible job explaining this, so let's do a question before we move on.
I think, okay, my main struggle with, I'm not sure what you're trying to get at, I think is why this was a bit confusing to me.
So my goal, okay. So my question for you is, if I give you a 2D device mesh, and I say, give me the PG for the intranode axis, how do you figure out what that PG should be? Remember, the PG says what nodes are going to be communicating in this situation.
Is that how DeviceMesh works today? It constructs a PG on the fly?
It doesn't do it on the fly because PG construction is expensive. You have to do communication. But yes, effectively, there are some PGs, and those are the ones you use in this situation. Go, Brian.
I also have this mental model that I have not confirmed, so maybe that's a good time to confirm it, which is, if I picture the 2D device mesh case, I kind of imagine that device mesh is implicitly creating 1 PG per row and 1 PG per column of the 2D device mesh.
That is a good intuition. There is one thing that I would add, though, which is that we have to say whether or not we're talking about a specific rank or what is globally happening everywhere. So in particular, if I'm working on rank 0, there are indeed 2 PGs created. There isn't a PG per row and a PG per column. There are only 2 PGs on rank 0. There's the PG that is the intranode PG that comms between 0, 1, 2, 3, 4, 5, 6, 7. And there's the internode PG, which talks between 0 and 8. Go, Chin.
Yes, I think what it was say is correct, but for PG correction, there's a limitation is all the ranks must participate when creating this PG, even though this PG is not used by this rank, or like this PG is not in this, this rank is not inside this PG. So essentially, when we actually created some sub PG or some mesh, we actually need to go through each row and each column.
Yeah, sorry. This is a wonderful correction, and you are absolutely right. So there is a API you call to create these sub PGs, because like we often talk about a global PG, which involves all of these ranks. And when you do this API call, you actually don't do this thing that I said, which is 0 to 7, 0 to 8. You actually have to pass in. So when we're creating the intranode PG, you pass in a list 0, 1, 2, 3, 4, 5, 6, 7, and a list 8 to 15 in this case. And similarly for the internode, you pass in 0, 8, 1, 9, 2, 10, and so forth. Goji.
I understand. Are you saying that for a in-dimensional device mesh, you create MPGs based on the coordinates? Like if you have a coordinate IJK, and then you have 1 PG on the I, 1 PG on the J, 1 PG on K, or is it the other way?
Yes, from a user perspective, however big your device mesh is, how many DIMMs it has, that's how many PGs you will in practice see on your node when you're working with things. And there are some exceptions, like when we talk about flattening and multiple meshes, but this is a good first approximation.
And each of the PG is always going to be one-dimensional, right? So you're not going to say, reduce 3-dimensional to two-dimensional, but you're actually doing 3 one-dimensional PGs, right?
So when you talk about what your rank is actually going to communicate with in the end, So there's like not really a dimensionality to the communication operations you do. Like when I'm doing an all gather, semantically, I'm just, I have a list of nodes I'm going to all gather from, and I'm going to concat all stack. I forget which one's the right one. I'm going to stack all the results together to be my result tensor. Internally, there might be some hierarchical communication going on because that's how the links work. But like that's the situation. Did that answer the question?
Sort of. I don't know all gather. I'm gonna look it up. Sorry.
So all gather is you have a tensor on every rank, and you just want to get all the contents from all the ranks, and you stack them together. There's another question. I want to answer that question. The hand is down now, but I want to answer that question. Yes.
Oh, it was me. So earlier you mentioned like if I'm like indexing into, or if I'm rank 0, I have 2 project groups. I have like basically the whole x-axis, but then only 0, 8 as the other group. If I wanted to have like 0, 9 as a connection, would that have to be a third dimension?
This is a great question. So I'm going to ask you a question in return, which is why do you want 0 and 9 to talk to each other in this 2D mesh? Are you thinking you've got a more complicated mesh and they want to talk together? Or are you just like, is this a thing that people do?
The latter.
Okay. You would never have 0 talk to 9. It's just weird. Like, in principle, the PG algorithm can let you do this. And I guess, Natalia, correct me if I'm wrong, but like for the torus style, like, stuff, you end up with weird connections like that, I guess, on TPUs. But,
probably still no, 0 to 9.
Still no 0, okay.
You would do 0 to 9 only if you are broadcasting your zeros value to everyone, including 9.
Yeah, that would make sense to me. Go, Sherlock.
So like, let's say you have a cube of a 3D mesh.
Yeah, excellent. Let's do it.
Okay, let me just finish the question. Like, should I think of it like, are you doing, like, let's say you want to create a PG on one dimension. Is it going to involve the whole slice of that cube or just one, like, cube?
Wonderful question. I love this question. This is an excellent question. Okay. So, let's do the example. So let's, did people like having the intranode, internode distinction here? Was that helpful?
I think that's like to put it in a more intuitive, like, physical thing is like, can you do like 2 by 4 by 2? Like basically you have a
yeah, let's do 2 by 4 by 2. So we're doing a 2 by 4 by 2 mesh. So basically what we've done is we've taken the 4 GPUs, split them into taken a node, split the nodes in half, and then we have
2 nodes.
Yeah. So let me go ahead and just copy paste this.
So short answer, you're generally communicating only across a single dimension, it's tube. But longer answer, at some point you will invariably want to flatten your mesh for one reason or another, and then you would be communicating across slice.
Okay, then the follow-up is like, do you create one PG group for that or 2? Like,
when you flatten, you'd need to create another flattened PG group and so on.
Tube is a line, slice is a plane in 3D?
yes.
Yeah.
Yes.
Nunha, is this like reasonable like names to assign for parallelisms, or is this like weird? You would never do CP on internode.
You do CP
Intranode.
on intranode.
Sorry, intranode. Would you ever do CP intranode, or is this just weird?
It's weird.
Okay. Do we ever do that? Like, so what would I do here then? Like TP and usually TP is all the nodes.
Just call them not XYZ because that's taken, not M and K because that's also taken.
Let's do IJK then.
Yeah.
Okay, we'll do IJK. Okay, so Sherlock, did you understand Natalia's answer, which is that when I do a com on the I axis, it's still 0, 1, 2, 3.
Yeah.
Now, I can do a com on I and J, in which case it would be 0, 1, 2, 3, 4, 5, 6, 7 on rank 0. And
Really sure.
most of our APIs don't let you specify these two axes together, although Jax lets you do that. But we do have a PR from Junjie, which merged, I think, which lets you flatten. So when you flatten I and J together, you would then end up with this device mesh. And you can see that clearly the flattened dimension covering I and J is the entirety of the intranode. Yes, MPK.
Yeah, thanks, Ed. So I have a question about Monarch. I'm curious for your thoughts about Monarch device mesh. I can postpone this till later if you want to further motivate or answer questions.
Go ahead and ask, and I'll let you know if I want to postpone.
Yeah, so I think, as you know, to some degree, and as I'm sure many know, Monarch has its own concept of device mesh, which is very similar. In that, descriptively, we use this concept of a named ended device mesh. We have similar operations like flatten, join, split. I think mechanistically, especially around Dtensor, they start to differ. But from an interface perspective, I'm curious from your understanding of what Monarch is doing, are there any differences that are worth calling out? And I guess seconded to that is there a reason these shouldn't show the same interface, if not the same implementation of how users interact with devices?
Okay, so this is jumping ahead, but let me just try to answer to the best of my ability. So I think, to me, the biggest difference is that Monarch wants to deal with NPMD, wants to deal with fault tolerance, and both of these sort of work a little. It was a little strange to like shove them into an ND tensor mesh type thing. I do think that if you're in an SPMD world, this feels like the right way to do the organization. I can't think of I want to do SPMD, but my communication structure isn't representable as an ND tensor. So that maybe you can argue differently, but that is a conviction I have. But yeah, when you get into NPMD world, you get into fault tolerant world, you need to do something else. But I also don't think device mesh is a super you can think of a more abstract version of device mesh which can handle this case, but I haven't really thought about that. Go ahead and respond if you want to respond.
Yeah, so I agree that mechanistically, the Dtensor, the process group comms might be different. But this is where I said, from interface perspective, even in many NPMD applications, such as pipeline parallelism, you might want to still have a named pipeline parallelism dimension. Or for a fault tolerance world, you might want sort of an outer replica FTAR sort of data parallel dimension. So my, I guess, thinking is that from a descriptive perspective and manipulating this device mesh, it is still relatively similar, even if you want to decouple the mechanism implementation.
I guess my point is that the model of so what you are calling implementation, aka the model of device mesh as an ND tensor, there's sort of this interesting thing where sometimes the implementation is the semantics, right? It is really useful to be able to conceptually think of device mesh as an ND tensor. And so I don't think you're going to be able to convince people to not think of it that way. You're going to be doing a more abstract, more encapsulated concept that shares some things from it. But I think a lot of people are going to still think about things in terms of these, ND tensor meshes, because it is a really useful way of thinking about it.
One point, it's not just really useful way. If you are not thinking about your meshes and Dtensor, then you are in for a world of trouble. And one example I have is when people are trying to implement, for example, collectives or very big meshes, DP meshes that have some weird sizes, and they want to use hypercube algorithms because that's typical effective algorithm to use. they end up creating phantom nodes just to be able to view this thing as an ND mesh that can be hypercubed. Seen that happen. So if, for example, your mesh is 17 and you want to implement a hypercube algorithm on it, then you need to pad it to 32 and work with your phantom nodes that have no data, contribute no data. And that way the algorithm is nice, and if you try to just implement it in 17 way, you will fix one bug, second bug, third bug, and then decide, screw it, I'm going to 32.
Yeah, so I have a follow-up question, but Alvin, if you want to jump ahead, feel free.
No, go for it. It's a different question I have.
Yeah, so I agree it's useful to think about it as an ND tensor, but I would argue, and I'm curious, Natalia or Ed, if you think differently, that this is also what Monarch is doing, meaning Monarch's device mesh is also thinking about this as an ND tensor, in that if you use the tensor engine or distributed tensors and you place a tensor on a device mesh of these dimensions, it exists and can be thought about as an ND tensor. I think that the process groups and everything can be different, which is why I'm differentiating the implementation. But conceptually, an ND tensor. Curious for your guys' thoughts.
I don't know if you've got one, Natalia.
No.
My best okay, so if you're right, then it's great. We don't have a problem. But I was I'm learning device mesh. It's beautiful, and now I have to learn about fault tolerance, and fault tolerance is not beautiful, right? So if I'm doing fault tolerant FSDP training by having replicas of FSDP, then what I'm doing is it's one of my replicas is down, so I'm gonna kill it. And then, so yes, I can model this as a device mesh, but my device mesh shrinks. I used to have 32 replicas. Now I only have 31 replicas. And it's just so go ahead.
Yeah, so one, I would say this is not so fundamental. I think the thing you can think about, which is not optional extension, is things like joining two device meshes together. So you can have sort of fault domains.
Oh, we want this too, by the way. There's a semantics for joining submeshes, which we can talk about eventually.
But I would argue from this conceptual perspective, it's not fundamental enough to worry about. And
okay, so maybe we're fine. So I would be happy if we're fine. Go, Albin.
There was a side question. I wanted to ask you to explain your annotation for the device mesh collectives here with the axis XY.
So are we talking about this? Yeah. So all right, so let's just talk about what I'm laying out here. So when I do a collective, and if I do the collective in the JAX style, actually, how do I want to explain this?
Can you explain what the JAX style is, if that's going to be key?
No, yeah, I'm just maybe I don't want to explain what the JAX style is. All right, let's imagine a counterfactual universe where our low-level collective operations didn't take in PGs, but they instead took in axes of the device mesh. Okay? And so when you say, I want to do this collective on this axis, you're saying, I want to do the communication between these nodes. So in this situation, you can just think of, if I just say I want to do it on X, then I do 0, 1. And if I just want to do it on Y, I do 0, 2. But when you do it in this style, it's also reasonable to ask the question, what if I do it on multiple axes at the same time? And this is not an API that Device Mesh directly supports, but it indirectly supports it. Because what you can do is flatten these two together, creating a submesh with two dimensions, flattened together into one, and then you say, okay, I want to do my communication on that device mesh. What device mesh lets you do is it says, give me the PG for an axis. That is the most widely used API on device mesh.
Okay, so what's the arrow?
Okay, let's talk about this.
Right.
So this post was not actually about explaining how to get from a device mesh access to local ranks. It's about given a set of ranks which are participating in a collective, can you figure out what the other ranks are doing in the situation? So if I'm rank 0, I'm participating in a collective 0, 1, 2, 3 when I'm doing a comm over everything, and there aren't any other collectives going on. But if I'm doing the communication between 0 and 1, it turns out that it's also another collective is going on. Well, they're the same collective, but like there's another group of ranks talking to each other, 2 and 3, going on at the same time. So this is where, like, you know, when we're thinking about just what one node is doing, there's this line and this other line. But when I think about globally what communications are happening, well, there are 2 lines, a line here and a line there. People often refer to these as fibers because, like, you know, if you think about like what's going on when you communicate I in a 3D mesh, it's this, it's this, it's this. Sorry, it's this and it's this, right? So you can think of there's these 4 fibers, these 4 sticks, and you've bundled them together, and that tells you what communication is happening on the mesh. I find this geometric intuition very, very helpful. So, like, think about it.
Okay.
Any other questions? Yes, Brian.
I guess this is more, or okay, you're talking a lot about the mapping between the device mesh as this ND tensor and the set of process groups that we create. And you also talked about how in the like 3D example, we create a process group for every like pipe of that a given rank intercepts with. And I guess it sounds like you can end up with a lot of process groups, especially if you like flatten every subset of dimensions you care about. And is this a problem? Like, do we in practice need all the process groups that you could create, or do we like lazily create them or something?
Yeah, this is a great question. So remember, if you only do a 3D mesh and you have 3 axes and you're not doing anything weird, you're only going to end up with 3 process groups. You're actually going to end up with a lot of process groups when you look at the entire cluster, but on your node, there's only 3. So, it's probably okay. That being said, when you're doing really complicated parallelism, like in Torch Titan, they are doing this thing which is like PP, DP replicate, DP shard mod EP, DP shard and EP, CP, TP. Some of these are like virtual DIMs, which you never actually want to communicate on, but they need to exist because you're going to flatten them. And you're going to flatten them differently in different situations. And so these end up being hyperplanes on your device mesh, which sometimes share axes. And so it's useful to not create the PGs for the atomic dimension, which doesn't matter. But we're going to have lazy PG initialization, so it's fine. The PGs won't get initialized until you actually try to do comms. Did that answer the question?
That answered my question. Well, okay, that answered that specific question. I have this other tangential question around autoparallel and like how we decide what process groups to use. And like handwave seems like a very large search space. But...
Okay, I'm going to answer that question after these other questions. Yes, go ahead, BK.
Yeah, so if you are using device mesh without Dtensor, are process groups created? My understanding.
Yes, the whole point of device mesh. Like, the original conception of device mesh was, man, it's really annoying creating all these process groups by hand. And then, you know, device mesh makes it easy to create the process groups.
Okay. And so they will be created, but they will be lazily actually...
So I don't know if this actually landed. Maybe Chinchin knows. But they will be lazily created eventually. So they only show up when you call.
Wait, but that's not a good thing, because Excel-formers actually is moving to eager init, and ptcoms is moving to eager init, because calling your first com and discovering that now you have to sit idle for half an hour and your timeouts hit on other things is not a great experience.
Yeah, here I need distributed people. I don't know if we have... yes.
So there are 2 things. Like, first of all, yes, we actually as a people to init our device mesh, including some mesh upfront, so that we can know, like, for example, timeout, everything like happen in the very beginning. Second is for the new device mesh design, we actually separate the device mesh concept from the PG creation in the implementation. So there's a device mesh representation, there's a PG, it's actually PG creation. So I think these two concepts are actually separate. So we can create a device mesh without actually initializing PG, but we can force device mesh to eagerly initialize PG when user wants to do that.
And what's the API for that? Do I just give all the axes I want?
Right now, the API is not finalized yet, but yes, I think that will be the case.
Okay, go Natalia.
You'd need to submit the axes because otherwise, as previous example shows, you don't even want some PGs for single non-meaningful dimensions, and you don't want the PGs for all the possible Flatten combinations because that's combinatorial. So you need to tell it what to do.
Go MPK.
Yeah, I have the same. I think the ideal here, in my opinion, would be to lazily create by default, and if specified, you can specify the non-phantom dimensions you want for eager creation. I think that's the same thing you're saying, Natalia. But
yeah, there's a lively API discussion about how exactly to do it, because there's no obvious API for this, I would say. Let me think. Okay, so let's answer Brian's question. So Brian asked a question about auto parallel. No, I'm not going to answer your question yet. I want to talk about Dtensor. Let's talk about Dtensor. Okay, so we spent a long time talking about device mesh. We talked purely about how communication happens. But the only reason we're doing communication is because there's a relationship between the data stored on all the nodes. And how exactly do we describe this relationship? Well, this is what Dtensor is for. So the idea behind Dtensor is it gives us an ability to say, well, I have a tensor, it has a lot of data, like maybe it has a batch dimension, and I don't want to store all that data everywhere because that takes a lot of memory, and it means I'm not really parallelizing anything. What I want to do is I want to split the tensor into shards and then distribute those shards over devices in my group. So the device mesh concept is clearly useful because the device mesh helps us say, okay, how exactly am I distributing the shards to the GPUs that I have? So we're going to introduce the concept of placement. And placement is going to talk about device mesh and tell us how a tensor is split up among the GPUs on our device mesh. So let's go back to the 2D example. And let's just look at a normal data parallel situation. So let's say I have a tensor, which is batch. And then let's do something simple. And then there's a bunch of tokens. And so the way that PyTorch does placements is different from the way JAX does placements. And the way we do it is we say, for every dimension in the device mesh, tell me which dimension on the tensor I shard on. So if I'm in a data parallel situation, my device mesh is going to look something like replicate shard 0. And let's explain what this means, okay? So these correspond to dimensions in the device mesh. Because the convention in PyTorch is the contiguous dimension is on the right-hand side dimension, this translates into internode, intranode. So this is the annotation for internode, and this is the annotation for intranode. And so what am I saying? I'm saying, well, take this tensor, and this tensor is a 2D tensor. Go ahead and on the batch dimension, that's the 0th dimension, split it up so that, wait, why did I do it this way? This is wrong, sorry. Well, let's say we're doing like dp on the outer dimension and tp on the inner dimension. Sorry about the typo. Okay, so what we're going to say is take this tensor and split it so that half of the tensor is on the on node 1 and half of the tensor is on node 2. And then when we say replicate on intranode, we say, well, this split tensor, every GPU in the node has a copy of that tensor. That was also a horrible explanation. So let's take questions. Go, Jacob.
If you had like a pipeline parallelism, how do you say like it's not?
You can't. So pipeline parallelism is MPMD. So you cannot express that with a D-tensor abstraction. So what you typically want to do is you have your device mesh that has pipeline parallelism on it. You want to like get rid of it. So you have a submesh, but this is not actually what we mean by submesh. So woo! And then talk about that. This is what we mean by an SPMD mesh. Like you have to actually be SPMD for all the nodes. Go, Simon. Go, Alban.
Just to say, I think if you make the tensor not 2D, that will avoid some confusion.
Okay, so I don't know, batch, tokens, feature. Yeah. Oh no, it's the same. This doesn't change.
Yeah, that's why.
This
why,
doesn't change.
So.
Yeah, there you go. Go, Simon.
Can I shard more than one dimension on a device mesh div?
Yeah.
Or do I need to create a new device mesh div for that?
So actually, okay, there are two ways. I think you meant, okay. Let me answer your question as is, and then I'm going to answer a different question, which is sort of analogous. So the question, I believe, was basically this internode dimension. Can I have it shard both 0 and 1, maybe? Like maybe some sort of context parallel type situation? And the answer is no. You cannot do that. But what you can do is you can split the device mesh into a 3D device mesh. And now you can say, okay, well, K is going to be my data parallel shard on batch, and J will be my context parallel shard on tokens. You would never do this. So I need to like make a bigger mesh so that I have 2 dimensions on the outside of the inner node. But like, we're just doing examples. So like, please pardon the unrealism of this particular example.
Or alternatively, you could flatten your tensor so that 2 dimensions that you wanted to shard on this mesh dimension become 1, and then you are within what API supports.
Exactly. Go, Alban.
But for the 2D mesh up there, you could have shard 0, shard 1.
Yes. Yes.
Right, yeah.
So let's talk about some other cases. Actually, Sherlock, if you've got a question on this, let's do this question first.
Yeah, like, can you clarify like what it means when you have a 3D tensor but like 2D mesh? Like, are they left aligned?
No,
Like,
they do
example,
not align. So the tensor dimensionality and the mesh dimensionality are completely decoupled.
Yeah, so for this particular example, when you have a 3D tensor and about like 2D mesh, like, does the replicate applies to second and third dimension?
Oh, that's a good question. So, I mean, it applies to all the dimensions, I guess, if that's the intuition you want. I don't think of it that way, so I'm not sure how exactly. But yes, it's like all the dimensions.
Like, Sherlock, the first one could be shard 1 and replicate. That would be valid as well.
Yeah, so this sounds like it's just...
So you can view like a replicate, you don't have the dimension, but for shard, you need to specify which tensor dimension you need to shard. So
Actually, no, I have an explanation. So another way to think about this is when we're writing a placement like this, we're defining a function that takes your original tensor and splits it into a bunch of chunks, right? And so there's a very interesting mathematical property about splits, which is it doesn't matter what order you do them, right? I can split the cake vertically and then horizontally, or I can do it horizontally and then vertically. And so for any given... So basically, the way that we've modeled it is we say, okay, for each device mesh, you get a chance to split the cake, right? So internode gets a chance at saying, okay, I want to split it this way. And then intranode says, I can split it or I cannot split it. And so when I say replicate, I mean don't split it. And then there's a way of assigning the pieces of the cake to the resulting GPUs.
And I think this is a good time to introduce Jack-style notation.
Yeah, okay, let's talk about Jack-style notation.
Find the PyTorch style notation unintuitive, and there is one-to-one correspondence. And actually, 6lib is writing their tests in like Jack-style notation, and then they have a function to transform the Jack-style into PyTorch style.
So let's talk about Jack-style notation. So So this is how I would write the placement in JAX. So unlike PyTorch, which is per device mesh dim, JAX is per tensor dim. So what do I do? Well, for every dimension in my tensor, I have an annotation saying what device mesh axis I split it on. So I say split batch as many times as there are internode, and don't split tokens and don't split feature. And so you can see that you can convert between these two, except some exceptions, which we can go into if someone asks a question. But we're running low on time, so I just want to answer questions now. And it matters who you specify here, because this tells you how many splits you do, and it tells you where the splits end up going, right? You split by however many the size of the device mesh dim, because you're going to distribute it among the devices on that device mesh dim. Okay, so I want to make a point about pipeline parallelism and submeshes and things like that. So, actually, no, I don't. No, I want to answer more questions. Let's go through some funny other business. Okay, so Albin suggested we try some other examples. So let's take a look at this very unrealistic example: shard 0, shard 1. So what is going on here? So this is sort of typically the situation when people draw the sort of classic diagram that looks like this. I cannot draw this diagram quickly. So imagine a box. Sorry, I need to go back to a simple mesh. So we're doing an entirely new example. The device mesh is a 2D 2x2 mesh. Confusing, yeah, I know. And my tensor is like this 2D tensor, because that's the easy thing to visualize. And what I've done is I've split it into 4 pieces. And now I signed it. So I said, okay, well, this chunk of the tensor goes to GPU 0. This chunk of the tensor goes to GPU 1. This one to GPU 2, GPU 3. This is a very classic way to like explain what sharding means. And so let's try to figure out what the PyTorch placement describing this is, okay? So the PyTorch placement, the device mesh is going to be 0, 1, 2, 3. So we're sharding on both. And so for the innermost device mesh dimension here, we're sharding on 0, because this is the 0. Going left to right is the 0. See, I messed this up. 1, because you're sharding on the dim 1 of the tensor. And this one is 0 because these cuts are sharding on dim 0 of the tensor. Okay, so pop quiz. What does the diagram look like for shard 1, shard 0? Natalia, you don't get to answer because you know this. Yeah. Anyone else?
You transpose it?
Yes, it is transposed. Let's just work through this, okay? So we said that for the device mesh dim 1, sorry, dim 0, aka 0, 2, we're going to shard the dim 1 of the tensor. So 0, 2 goes this way. And for device mesh dim 1, aka 0, 1, the innermost dimension, we're going to shard on 0. So it goes 0, 1, like that.
What are the JAX equivalents?
Yeah, let's write the JAX equivalents. So supposing our device mesh is just called, what were we using? Internode, intranode. Then you would have placement on the 0th dim, aka the outer dim, shard on in. Sorry, this is I messed up. I don't. Let's just call them y and x. Shard on y and shard on x. And this one is shard on x, shard on y. I apologize if it looks reversed to people. Go MPK.
Yeah, my question is, does the JAX notation intended to handle non-SPMD dimensions such as pipeline parallel, or is it really for like the sharded tensor SPMD?
No, not really. It's equivalent. Subject to device shenanigans. Yes, Brian.
You said a second ago that this is not an example you'd see in practice.
Oh no, the problem is that like, you know, there's only 4 GPUs in your world, and like this is what, like, so if you want to make this more realistic, we're going to like do this all the way to GPU 7, and then we'll do this all the way to GPU 15, and then we can do internode, intranode, and then this is fine. And I haven't updated this one at all, so ignore it.
Sorry, this is like a noob question here too. Like, this is the placement applies to an incoming tensor, or like. So semantically, so the way to look at this diagram is whenever you have a D-tensor, it morally represents a really big tensor that none of the nodes actually have, but like in your head, that is what semantically the tensor means. And when you do operations on it, the operations are on this semantic full tensor. That's the term we use in D-tensor land. So when we are like, but actually you don't have all the tensor, we've split it up. You take the tensor and you slice it up, and then you say where you put all those things, and those are the GPU numberings. So that's what these diagrams are about. And so tile 0, 0 goes onto GPU 0, tile 0, 1 goes into GPU 1, and then in the later case it would be transposed.
Yeah, that's right. Any last questions? We're almost out of time. Okay, so just some fun tasters. So you can also do this. And this in JAX looks like this. And so what this means is that I want to shard the 0th dimension of the tensor on the internode dim and on the intranode dim. So it ends up looking like this. And to make matters worse, this is not the same thing as this. This is a different thing. But you can't conveniently express that with the PyTorch notation. Question. Someone had a question.
Yeah, so at first I thought that the JAX and the PyTorch notations were effectively like there was no loss of information going from one to the other, but this feels like an example.
Yeah, this is an example where there is. And so the proposal is to add this thing, placement order, where you can basically say, well, on dim0 of the tensor, please order it internode.
Right.
This is a proposal in progress. It also goes in the opposite direction. So there's another form of placement called partial. And what this means is that on this axis of the device mesh, there is a reduction you need to do to get the real tensor. But we haven't done it yet. And partial always talks about a device mesh axis. And so you cannot conveniently express it in the JAX notation because you don't have, you need something like reduction axes equals, blah.
Does JAX not support that at all today?
They actually do, but I have been told that no one uses it and they have some other way of doing it. I don't know. It's kind of complicated.
For the previous one, is that equivalent to flattening your device mesh and then like, how do we call it, sharding on the new device mesh?
I never thought about this, but I think you're right, actually. So the problem is that in the intranode, internode order, you get this weird, jumpy order, which is not conveniently expressible. But actually, it can be done with cute layouts. But we didn't get to cute layouts, so I'm so sad. So too bad. Maybe next time.
I was gonna say for the flattening, you lose information, right? Like, if you go from like a 2,2 to a 4, then you don't know what the ordering of your two dims were.
Well, you do if they were contiguous, because then you end up with a nice 0 to 15. But if you had transposed and then you flatten, then you have this weird order. And like in normal PyTorch view ops, you can't transpose and then flatten. You have to do the reshape in this case. But you don't have to with cute layouts. So stay tuned. Okay, we're out of time. I'm going to let everyone go. Thank you for listening to this lecture on Device Mesh. And yeah, see y'all later.